Well, hi there. This is going to be the second video in Unit 9, and I made this really just as a supplemental video, hoping to just kind of reinforce some of the information. This section is going to cover network atomic solids, and it's also going to go into a little bit of metallic solids. Now, silicone and carbon actually make some of the coolest solids, and they're called networks. And the reason why they're called networks is because they end up making these giant molecules. And I know I've talked about them in class a little bit, but diamond is considered a network solid, as is glass and quartz. These are all made from carbon and silicon, and as you can tell, they're in the same group, so they have a lot of the same properties. And one of those properties is to repeatedly bond to itself over and over and over again. Now, typically these giant molecules are pretty brittle, and while even diamond is the hardest substance we know, that doesn't mean it won't break. It can be very brittle when it is very hard, just like a lot of metals. If you can think about how some of them can bend and mold, but if we make them stronger or harder by putting carbon in them, that oftentimes can make them brittle. So they do not conduct heat and electricity in general. However, some allotropes of carbon, graphene in particular, do conduct electricity. So we'll start with the carbon side of things. Two common forms of carbon are the diamond that I just talked about and graphite. And graphite, I'm sure you've seen, it's packed in your pencils, and it doesn't quite look like carbon like diamond looks like carbon. They are obviously very different in that shape, in that sense. But what's really different about them is the bonds. In carbon, we see repeated sp3 bonds, which means they are single bonds repeatedly bonded to or carbons repeatedly bonded to itself in a tetrahedral pattern that's repeating over and over again. Where graphite is actually in a hexagonal, almost like a honeycomb shape. And it's slippery. It's actually used as a lubricant for locks in industrial settings. And obviously, we have a difference in color. And it just so happens that graphite is also conductive, just like graphene is. So diamond, like I said, each carbon is surrounded by another carbon in a tetrahedral pattern. And because they are sp3 hybridized, there's no way for the electrons to travel. They're all locked into those single sigma bonds in between the carbons. So there's no conductivity whatsoever in terms of heat and electricity. Now, most of the diamonds that we see are not as pretty as the one in the picture there. Most of them are actually used in industrial settings on blades and so forth, cutting instruments. But you can actually make a diamond, and there are some companies that now make diamonds out of carbon. In fact, it's a little morbid, but some of these companies actually make diamonds out of the cremated remains of loved ones. It's kind of interesting, but if you can imagine, to break the bonds in a graphite in graphite, you have to apply 150,000 atmospheres of pressure at 2800 Celsius. I mean, those are some really, really strong bonds to try and rearrange into a diamond structure. So as you can imagine, even the ones that are made in a commercial setting, they're quite expensive. So graphite is also very, very cool allotrope of carbon. It has 6 carbons all fused in a ring, very much like a honeycomb pattern. And these actually have an sp2 hybridization. So that means I have an alternating pi bond through this honeycomb, just like graphene. And these unhybridized p orbitals, or these alternating pi bonds, allow for the electrons to delocalize. In other words, they're not locked into the bond, and they can travel throughout the molecule, which is really, really cool. So just to kind of compare the two, this is what we would see with diamond. Again, you can kind of see these individual tetrahedral shapes all into this giant molecule, and it can really repeat itself as many carbons as you want to add to this. Whereas graphite here, we have these really, really strong bonds within the honeycomb. So all of these are these alternating pi bonds in the sp2 hybridization, but there's these weak attractions between them, which means that this plate right here will slide back and forth across this plate and this plate here. So this is where this becomes a really good lubricant for locks and so forth, because all these plates will slide past each other back and forth and still remain stable within the honeycomb itself. So just another kind of look at this. This is just the graphite to show you that the p orbitals are still sticking up and below the plane. And so these are your unhybridized orbitals that allow for this conductivity band, or this conductivity through all the electrons to travel all through there, just like that. So silicon is just as important as carbon in the way that it bonds. And just like carbon is important to organics and organic chemistry, silicon is just as important to geology, because it makes up almost all of the Earth's crust. And again, we see this kind of repeated bonding phenomena that we see in carbon. So carbon usually has really long strings of carbon-carbon bonds. We see this in proteins and lipids and so forth, whereas silicon normally bonds and involves chains of silicon and oxygen. So we get something that's a little bit different, but it's still very similar in principle. Now, even though the empirical formula of glass and quartz is SiO2, it normally has an arrangement, just looking at the arrangement that it makes, is normally an SiO4. In other words, each SiO2 is kind of backed up by the oxygens from another molecule. So we end up with these very structured looking, almost, again, we've got almost like a honeycomb looking centerpiece, but we also have kind of stars sticking off of this. And so this is also why we see some of the shapes that we see in quartz, is this kind of repeated structure. Now, if I have, and this is called silica too, I didn't mention that earlier, but silica, or these silicone chains, can usually look very much like this when they are in our structured order. So this would be more like quartz. Now glass, and I believe I've mentioned this as well, glass is almost this flash frozen structure that you see with quartz. If you look, this is very disorganized, whereas this picture on top, this is quartz, and I see this, again, repeated, very organized structure. But when I melt this down, and glass ends up being what we call amorphous, and it looks truly like a frozen solid. And it's normally really described as almost like a homogeneous, very viscous solution, rather than something that's crystalline. So if it's crystalline, we see the structure, and down here we see something much more disorganized. And so this is why we see a difference in visual characteristics between quartz and glass. Now glass in general, the properties that we see in glass can vary quite a bit. Some of them have really high melting points, maybe some not as much. Some can be really, really colorful and beautiful. But a lot of this has to do with what we're adding to the silica. Most common glass we call soda glass, and it's normally greenish, and it has a sodium carbonate that's been added to it. So if you were to see window glass from the side, it typically looks green, and this is because they've added this sodium carbonate, or this soda, to it. Another one is a borosilicate glass, and that's when we add some boron to it with some oxygen. And that normally is something that we see in Pyrex or baking dishes. And it really just helps the glass not to expand and contract as much during large temperature changes. That way we don't break the Pyrex when we stick it in the oven and we pull it back out. And one of the last of the most common things that we add to glass is a potassium compound. And this really just hardens the glass quite a bit, so it can be ground into shapes for lenses, or yes, back in the day, they even used hard contacts. Your parents would probably, if they wore contacts at some point, they might have worn hard contacts. And so this is something that's normally used for something like that. Now, the book goes into all these different compositions of different things that we can add to glasses. And really, I find it pretty interesting, just all the different things that they could use there, but obviously nothing that I would require you to know for any of the tests or anything. So silicas and silicates Silicates are normally the compounds that we talk about that are related to the silicas, but these are normally found in rocks and clays and soils and things like that, more earth related. And like silica, silicates are based on an interconnected SiO4, this kind of tetrahedral, but keep in mind the ratio is still a 2 to 1. And the ratio, sorry, instead of the 2 to 1, the ratio is typically a little bit higher uh, than the silicon oxygen that we have seen before. Now, silicates can range quite a bit. If you look here, we have the SiO4. Again, there's that higher ratio, Si2 to O7, and so forth. So these are silicates we tend to see in clay. So if you ever took a ceramics class or maybe worked with molding clay at some point, or even stuck your hands down in the ground, some of the red clay that we see down south, you're going to see some of this kind of stuff, and we see these again repeated structures. And if you have ever played with ceramics, you'll know that a lot of these things actually have almost like plates, like graphene, graphite, that they slide across each other. They're very strong in their structures, but then the attractions between them are fairly weak. So they tend to be strong yet brittle and can be heat and chemical resistant. So these ceramics, excuse me, are normally kind of heterogeneous as opposed to glass that's more homogeneous. And they have really two phases that are all kind of grouped into one mixture. We normally have these really small crystals, and then there's almost like a cement, a glassy cement. So it is definitely heterogeneous, excuse me, in terms of the mixture. It's just that they're all made out of the same elements. Clays that we, again, from the earth, that we see almost like a weathering, or a lot of these silicates are kind of worn down. And we'll see similar mixtures that we saw in the glass, some sodium, some potassium, or maybe even some aluminum. And really a lot of these just add some really pretty colors to some of the quartz and the silicates that we see in geology. Ceramics, though, in terms of some of the cool things about ceramics, ceramics are definitely considered a high-tech material. And in terms of material science and a lot of the things that we're starting to see in the future in terms of materials, these things are resistant to corrosion. They can handle high temperatures, and it makes them really cool for constructing car engines, jet engines, and even more recently, there's been a push to include them in something called organoceramics, where they can actually incorporate an organic carbon polymer into the ceramic, and it ends up allowing them to be superconductive. They can be used for prosthetics or even artificial bones. So there's some really cool stuff around the corner with ceramics. It's not just making vases and playing around with clay. There's some more things going on with that. And finally, the really cool thing about some of our silicones in particular are that they're semiconductors. And you probably already knew this, perhaps, that silicone is used in motherboards and some other computer devices to allow for some conductivity. And yet, what's good about them is they don't necessarily get hot. So they don't have necessarily the heat conductivity, but they definitely have the electrical conductivity. So at higher temperatures in particular, electrons get excited in the conduction bands. And if you remember, we talked about conduction bands in class. And because the electrons get excited, they jump up to these overlapping orbitals, and they're allowed to conduct back and forth between the atoms. Now, there are two big types of semiconductors that AP wants you to know about and be familiar with. And one is called an N-type semiconductor. And it's when I take a matrix of silicone and I'm going to take almost like a substitutional alloy, if you will. I'm going to take some of those silicone atoms out of the matrix, out of this crystal structure, and I'm going to replace them with arsenic. So I'm going to flash over here to my periodic table so you can kind of see where I am. So here's silicone, and I'm going to add some arsenic over here, And the one thing that I want you to notice, so silicone has 4 valence electrons. Arsenic has 5. So when I'm doing this, when I'm taking out the silicone and replacing them with arsenic, what I'm doing technically is I'm adding extra electrons to the matrix, to this structure, allowing it to conduct more electrons because it has more electrons to do so. Now the other type seems almost counterintuitive. I'm going to take some of the silicone atoms out of the matrix, and I'm going to replace them with boron. And by the way, when I do this, when I replace the atoms, boron or arsenic, this is called doping. Yep, that's the technical term for it. So when I dope the matrix with boron, again, let's take a look at the periodic table here. So here's my silicone, again, with 4 valence electrons. Sorry, did not mean to do that. And then I'm doping it with boron. So boron has less valence electrons. And this is where the counterintuitive piece comes in, because you would think with less electrons means less conductivity. But actually, by putting boron in there, it allows for an open hole because it has less electrons, so it has an opening in the orbitals. So basically, it's allowing for a space for the electrons to move. So it's kind of like a vacancy that's allowed to be used. So here's my N-type conductor here. This is a visual from our book. And the electrons get excited. They can jump up to these conductivity bands, these excess electrons, and it allows them to move and be conductive. Now, rather than using the upper end of these conduction bands, when I'm doping with boron, they're just allowed to use or move from spot to spot to spot to spot, these openings that boron has left me. Now, where these things get, where this gets a little bit more interesting is when I back up an N-type to a P-type. And I get a PN junction. Now this was revolutionary. The reason why you can handle your phone in your hand while you see computer monitors that are slim and not those huge things that they used to have in the 80s and 90s, you see it's because of this PN junction. Because the biggest thing was we have alternating current. We have electricity that'll go one direction and it'll back up, and then it'll go in one direction and back up. And the electronic devices that we have can't handle that. They can only allow for electrons to go in one direction. So this PN junction basically allows for electrons to go in one direction and stops them from going in the other. So rather than electricity going back and forth, what we now have is electricity going forward, stop, repeatedly. And this allowed for a revolutionary changes in our electronics. So here's how it works. I have an N junction on this, or an N semiconductor on this side with my extra electrons from my arsenic. And then over here on the left, I have my openings from the boron. So when I hook up an electrical current to this, my electrons go towards the positive terminal. So as my electricity is moving to the right, all my electrons go over here. And I don't have any extra electrons in my p orbitals to go in this direction. Then when the current reverses, I have these electrons that can go forward into these openings and travel. But they can't go back because I have this excess negative charge from the excess electrons. So basically I have this moving to the p, then it doesn't go back. Moving over to the p, then it doesn't go back. And again, and there's several other slides. I won't go through all of them because I basically just explained it. But there's some more information on there in case you need a little bit more explanation. But again, pretty cool stuff. AP likes to hit on it just so you kind of understand how chemistry is actually changing the way we live. So I hope this has been helpful, and have a good evening.